right, in this section we're going to be talking about 5.1, which is solving systems of equations. We're going to start with equations in two variables. Notice these are linear equations. An x and a y variable, two variables, makes that linear. And we've graphed those in our past. And then another linear equation. You could actually graph these to find the solution. The solution is going to be where these two graphs intersect. The crossing intersection point is the solution. So if you're using a graphing calculator, feel free to do it that way. That is perfectly fine. We're also going to learn some methods for solving it with algebra, the substitution method and the elimination method. So you may prefer that. So anyway, you have options here. There's basically three ways to solve a system, either by the substitution method, the elimination method, so those are sort of algebraic manipulation methods, or by graphing them and looking visually at where the two lines cross. All right, so we're going to start this substitution, and again, even though the directions say to use substitution or whichever way you prefer, the answer is that's fine to use an alternate method. Okay, so first of all, but I will follow along just to demonstrate the different ways. With substitution, we threw four different variables. In this case, we have four variables, and we figure out the easiest variable to solve for. You're going to solve for one of these four variables, meaning isolate that variable. I would pick this positive y, even though you could pick any of them, but this would be my easiest one to solve for, in that I just throw the negative x across the line, making it positive x, and bring down the 13. So I solve for one of the variables, and then I sub whatever it says these two things are equal, right? So they're substitutable. Y is the same as x plus 13. So I substitute this in for the y in the other equation. So I drop that in for that y. That's the substitution. So now I rewrite it as 3x plus 4. Instead of y, I'm subbing in this x plus 13 equals negative 4. That first equation. So what that does is it gives us an equation that is solvable now in one variable. So we can solve it with our algebraic linear methods. So we get 7x's plus 52 equals negative 4. Solving that by throwing the 52 across the line, making a negative 56 on the right side. Dividing by 7, x is negative 8. Now that's only half the answer. The answer is an x and a y. You know, the point where they intersect needs to have an x and a y. So now we know what x is. We need y. So what does y equal when x is negative 8? You go up to your former equations, any form of that, plug in x is negative 8 for this x, or this x. Any of the equations, we're looking for what y corresponds there. This is the easiest place right here, but no, you'd get the same answer in any of the equations. So y will be negative 8 plus 13, which is 5, right? So y is 5, x is negative 8. Put that in point form, negative 8, comma 5. That's the point where two lines should intersect. Also, it's the solution. It's what works for this equation and this equation simultaneously. So you can check it. 3 times negative 8 is 24, plus 4 times 20, negative 24, plus 20 is negative 4. Okay, you can do that math and check that's true. Also, negative 8, which would be 8, plus y is 5. 8 plus 5 equals 13. So it's the one combo, the one and only combo that works for both equations, the solution. All right, we call that a consistent system whenever they do come out to just be that one crossing point. That's called a consistent system, which most of the homework is. All right, number 2. Do it again. On this one, they've already solved for a variable, so it's even a little better than the one we just did. We've already got y equals to start us out. So we can sub in the 4x for the y in the former equation. It's even more set up directly for substitution method. And then that's solvable for x. We get x is 4. So just like before, you find your x, you need its y counterpart. So we put in 4 for this x. Y is 4 times 4. That is 16. So the combo, the solution, is x is 4. Make sure you get these in the right order. Y is 16. Again, check it out. 3 times 4 is 12. 12 plus 16 is 28. Also, if I plug in 16 here and 4 here, that is also true. 16 does equal 4 times 4. So it works for both. That is the idea, the whole idea of this solving systems. The one point that works for both. Okay. Number 3. Also using substitution here, I'll keep with that theme. Notice you can solve for any of the 4 variables in your 2 equations. Sometimes I like to label those equation 1 and 2. That's kind of optional. But you do have 2 separate equations going on here. And you want to solve for one of those variables. Totally equal work here if you solve for this x or this y, because they both have a positive 1 in front of them, and that's kind of what I look for with substitution if there's a 1 in front. I'm going to do this x so that 1x or just x equals, throw that across, negative y and 1. Then I sub that in for the x in the other equation, right? So that's substituting for whatever this x value that you solve for, x or y, whichever way you did it. Then you can rewrite that as 5 equals 7. Instead of this x, drop in your substituted value x. Solve that routine equation. So distributing, doing our equation solving. Get our y's to the same side, so that bring that over. We'll have 12y equals 12. Divide both sides by 12. Y equals 1, right? So now we've got the y variable solved for. We need to know what x is when y is 1. So you go up to any of these former equations, but here's the easiest place. When you use substitution, at least that is kind of a perk of that, is you have a nice little solved equation already to drop that in. So y equals 1. There's a negative 1 there, so negative 1 plus 1 gives us x equals 0. So the solution is x is 0, y is 1. We can place those back in for the x's and y's. As always, like I've said in the early ones, check it out. Make sure it works. These are very checkable, right? Okay, number 4. Number 4, the directions say to use the elimination method, although, like I said, you use any method you want on these, whichever one you find the best. Okay, but elimination is where we try to eliminate by adding down the columns, either adding the x's or the y's, such that one of the variables drop out, so that you create an equation, like we did here, create an equation that's solvable, that only has one variable. So when you add your equations, we're allowed to do that and create an equation then we can work from to solve. So this one's ready to roll. If we add it just like it is, which doesn't always happen, we'll see. But this one, if we add straight down, the y's are already opposites. So when we add 2x and 1x, that's 3x. These y's drop out. 4 and 59 is 63. Then that's solvable. Divide by 3 on each side and get 21. So again, you need an x and a y, so that's the x part. Now, like I said, we don't have that handy place now. Now drop that as 21 like we did in substitution, but it's still not too bad. You take it into either of the equations. This is the easier one, I think, so get the same draw. I'll pick that second equation, change x to 21 to solve for y. Or anyway, trying to fit 21 59, so you can just even look at it and think about that. But the math of that, the process, what is that, 38. So y needs to be 38. Then you write it as a point. X is 21, y is 38. Make sure you type it in x, y order. All right. Number 5, we're going to practice that some more. Notice on this number 5 example, if I add straight down, nothing would eliminate naturally. So that's not going to work for me just straightforward. I'm going to have to manipulate the equations a little bit. But if I were to take this first equation and times it by 2, and there's other ways to do this, but I noticed that if that were a negative 2y and a positive 2y, that would work for me. I could have also times by negative 3 to make that a negative 3x. And eliminate the x's. That works too. So it's really your design. You're just trying to get one of the variables to cancel out. So I chose this 2, and then whatever I choose to multiply by, I can't just times it by that one part, right? We have to distribute it to keep the balance and times it through the whole equation. So it's an equivalent equation. We haven't just changed its value. So doubling every term in that first equation is perfectly fine. It's still equivalent to what it was. And then that second equation, leave it as it was. And now we can proceed like we did in the last example. We can add straight down. That's 7x. That cancels, and that's 14. And then it's solvable by dividing by the 7. X is 2. So remember, we need its y counterpart. So how do we find y? We take x is 2 into any of the former equations. I promise, and maybe we should take the time so you can see that, but if you put the x is 2 here, 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 or here, well, these are exactly the same, but in any of the equations you will get the same result for y. So you just pick the whatever you're feeling. Always pick the one that looks maybe easiest to deal with. I'm plugging x is 2 here. Y equals 16. Do my equation thing. Get y is 7. So the solution should be the solution for those. And as always, we can check back and just see that it's so. 3 times 2 minus 7 is equal -1. And 2 plus 2, 7 equal 16. It's just the one point that makes both of the equations true. All right, number 6. Okay, number 6 here. So saying on whichever way that you want, whichever way you're feeling. This one's not going to be quite as friendly though, because there's no way just to multiply either one of these equations and get, like, I can't times 2 by something and get 3 unless it's a fraction or a decimal. So it's going to be tougher. And I can't get 5 and 6 to look the same quite as easy either. So I'm going to have to manipulate, or I prefer to just manipulate both equations. I can either make both of these a 6. You could times this by 3 and that by -2, for example. Or I could make both of these a 30. You're really kind of trying to think of the LCD, the least thing they'll both go into, to make these the same multiple. I like that these are already opposites in sign, so I think I would do it that way so I don't have to mess with a negative sign, and sometimes, you know, we make more mistakes by timesing through by negative, but you know, you could do it either way. But I want to times this first equation by 6 and the second equation through by 5. All right, let's see if I can do that. 6 times 2 is 12x. 6 times -5 is -30. And 6 times 32, that's what I was looking at. I don't think I know that off the top of my head, so let me type that in, is 192. Then the second equation, I'm multiplying through by 5, making that 15x, 30y, and -30. Now we're ready to roll. These are equivalent to their former equations, just times through by a multiple, so that's perfectly fine. But now I've got something that I could work with. That will cancel out when I add. So I have 27x, and 192 minus 30 is 162. Divide through by the 27. I haven't used my calculator there for sure. And that is 6. So I get x is 6. Now don't be fooled to thinking they always have to come out perfectly even. You could get a fraction answer, but usually they do regenerate out with common answer forms. So probably these even. But actually they wouldn't have to. Just don't do wrong. Yours doesn't come out even, but do like your work. This is 6. So what is y? Any of these former equations, I think I like the first one. So I'm going to 2 minus 5 2. Drop in x is 6, which 2 times 6 is 12. And solve through on that one. Let's see, that solves to be a -4. So y is -4. So x was 6, y is -4. Put that in that nice order. And then, of course, we should verify our x and our y, solve both equations. All right, I hope that helps.